Okay, it's my pleasure to talk to you today about... It's on? Okay. It's my pleasure to talk to you today about developments in formal proofs. Let me start out with a bit of an outline of what I would like to cover today. The first part of my talk, first I'll give just a general introduction showing some examples of what it is that we're going to be talking about. And after I do that, I'm going to talk about building a reliable system using whole light. I'll say what this is in the course of the talk. So just to get started, a formal proof is a very simple thing conceptually. You just put the axioms of mathematics down into a computer, the rules of logic into a computer, and then you don't accept anything out until everything has been checked all the way down to the foundations. Okay, so that's all there is to a formal proof. Very simple conceptually. Difficult to carry out, as we'll find out. The second part of the talk will be just giving you an idea of how advanced these systems have become by illustrating this with a particular system, COC, Formalizing Advanced Mathematics. And then finally, the third part of the talk is going to be more about automation. There's a great distance going from the foundations of mathematics all the way up to advanced areas in mathematics, and we need a lot of automation to make it easier for the user to carry this all out. So let me just say, as I just said, a formal proof is where you put the axioms in and verify everything from first principles. The first system that might come to mind is Zermelo-Fraenkel set theory, just because it's so widely used. But for various reasons, this generally is not the system that gets used in practice when this gets done by computers. So we have a lot of different choices of foundations that we might use. Some of them are better adapted for computer use than others. And so one of the decisions we need to make when we start moving mathematics from paper-based type argumentation to computer is which of the foundational systems will we use. So to show you what formal proof is not, I just copied a couple of pages from Thurston. Now, Thurston's a mathematician I greatly admire, but he's, as you know, an advocate of a very exploratory, experimental style of mathematics. And so just putting one of his theorems up here, you see how we need to jiggle things about to make things work, and how this is more of a recipe for the types of techniques that you might use in giving a proof rather than actually being a proof. So, in fact, if you look at the introduction to his book, there's an advisory to the reader. What good is a tinker toy set if the holes are filled in with modeling clay? In the present exposition, many of the holes or questions are explicitly labeled as exercises, questions, or problems. Most of these are not walking the dog exercises where the dog follows behind on a leash until the awaited event. You may or may not be able to answer the questions even if you completely understand the text. Okay. So I put this up just because sometimes when I talk about formal proofs, the response I get from mathematicians is that, well, this is what we've all been doing all along. We put the axioms down and we reason from the axioms and the rules of logic to give our proofs. But in practice, for many mathematicians, this is not how it is actually done. Okay, so in this introductory part of the talk, I just want to give you a few examples of what various people have actually done formally One of the most spectacular results was the formal proof of the four-color theorem. So this is quite distinct from the ordinary computer proof. Now you're really reasoning all the way down to the foundations of mathematics. In essence, you're proving that the computer code that runs to do the computer proof has no bugs. And you're proving this using foundational reasoning in mathematics. So this is a project that was started with the help of Benjamin Werner and then completed by Georges Gonthier about 10 years ago. You see, well, you don't really see much of the statement or the proof here. It's the actual proof of the four-color theorem here is tens of thousands of lines of computer code to carry this out. So there are two well-known proofs of the prime number theorem, the elementary proof of Erdős and Selberg, and the analytic proof of Adamar and de la Vallée-Poussin. Both of these proofs have been formalized, done formally inside formal proof systems. This again is work going back about 10 years. A group, Jeremy Avigad and others, did it in a proof assistant called Isabelle. That was the elementary proof. And then John Harrison in another system did the analytic proof of the prime number theorem. So to do the analytic proof, of course, you need to build up the theory of integration and Cauchy residue and so forth. And this has all been done formally all the way down to the foundations to give a proof of the prime number theorem. Just to give an example in topology, formal statement of the Brouwer fixed point theorem. This was also done by Harrison. You can so if you're not familiar with the notation of the formal proofs, it can look a little bit strange at first when you first look at a formal proof and the statement. Here we've got a function from Rn to Rn. S is a compact set, it's convex, it's non-empty, F is continuous on S, and the image of the function F on S is a subset of S. Then there exists an X in the set S such that F of X is equal to X. Okay, so if you read it out, it's pretty much what you expect from Brouwer fixed point in n dimensions. And this was a formalization based on Sperner's lemma, if you know that approach to the proof, done inside the system whole light. Recent result, this is just earlier this year. In fact, the paper is just about to be published. This is a proof of the central limit theorem, again done formally, this time in the system Isabelle. Again, it takes a little work to decode the way that it's written in computer notation. But so we have an X that's for our family of random variables, mu a measure, sigma is going to be our standard deviation, and S is going to be our sum of random variables. And then we have different assumptions that the random variables are independent, they're integrable, the mean of each one is 0, the standard deviation is positive, the random variables are square integrable, the variance of all of them is sigma squared, they all have the same distribution. And then we get a weak convergence result for the sum of the random variables to the standard normal density. So again, this would be a project involving tens of thousands of lines of computer code to show everything from the foundations all the way up to the formal proof of this result. So I'm not sure of the proof that they followed on this. So this is a project, this is a big collaboration that I've been involved in to give a formal proof of the Kepler conjecture on sphere packings, which asserts that the greatest possible density of a sphere packing is that of this pile of oranges that you see, pi over the square root of 18, about 74%. I've written up the statement of the conjecture. There are these ampersands that appear in the statement. Like you see the square root of 18 has this ampersand in front of it. That's because in this formal proof system there's a distinction between the natural numbers and the real numbers, and you need to explicitly embed the natural numbers into the real numbers, and that's just the notation for the embedding. So that's going to appear in various slides that I show. And mathematicians wouldn't write that down, but it shows up when you write things down formally inside the system. But the statement is if you just have a packing, then there exists a constant that's giving the error bound for all possible choices of radius bigger than 1. The number of points in the packing inside a ball of radius r is at most pi times r cubed divided by the square root of 18, plus an error term that goes away as you go to infinity. So right now there are 4 assumptions. 2 of these assumptions have been taken care of, but the project is not quite complete. There are these 2 assumptions marked in red that still need to be taken care of. I gave a talk about a month ago here where I said the main thing that's left is I need 20,000 hours of computer time to finish this off. And Georges Gonthier was in the audience and talked to Microsoft and said, and they got me a grant on their cloud computer, and last week we ran 25% of this calculation, of this 20,000 hour calculation. So it's looking very promising now that with the cloud, a big calculation like that can become fairly trivial. The talk after this by Coquin is going to be all about dependent type theory, so I'm not going to go into any real detail about it, but I just have this one slide saying there's a foundational system called homotopy type theory that's been under very active development for the past several years. There was a special program at the Institute for Advanced Study during the 2012-2013 academic year, and during that period there were a lot of really nice advances in the formalization of homotopy, of results in homotopy theory. So I've just put one slide up here. This is, I pulled this off Dan Grayson's GitHub development. This is giving the definition of classifying spaces inside homotopy type theory, all done from this formal point of view, going down to the foundations. And it's just really remarkable. He has like a very short proof here of the connectedness of the classifying space. And during this period and recently, a lot of interesting results have been done in homotopy theory, including calculations of various homotopy groups of spheres, Seifert-Van-Kampen theorem, Freudenthal suspension theorem, Blaker's Massey, construction of Eilenberg-MacLane spaces, and just it's really making great progress with this foundational system. Okay, so that is the introduction, just to show you that we can really do some mathematics inside of these systems. And now I'm going to go back to the first point in the outline, and that is building a reliable system to do mathematics inside a computer. And for this, I'm going to use a particular foundational system called HOLES. The reason I picked this particular system, well, I'm quite familiar with it, but also it's really one of the simplest systems to describe. So this first slide is going to be about naive type theory. Now, the talk after this is going to be all about type theory, so I'm not going to go into any real depth about what type theory is, but from the naive point of view that I want to take in this talk, you should think of a collection of types as being, say, a countable collection of non-empty, disjoint, finite sets. Okay, so we just have a disjoint collection of sets, and these would represent things like one set might be the integers, and one set might be the set of booleans, and another set might be lists, and another set might be functions from one set to another. So set theory is completely amorphous, right? You have ordered pairs are a set, and functions between sets are sets, and no matter what you do, you're always in the world of sets. But with type theory, we're going to structure things into this collection of disjoint types, and everything is going to have a unique type. Okay, so I just gave one simple example of what we might think of as a type system. One would be, say, the Booleans with a true and a false. And our other basic type might be an infinite type, say the natural numbers, 0, 1, 2, 3, and so forth. And then recursively, we're going to build up more types as the functions between types that we have already. So since we have Booleans, then we'll have all functions from bool to bool. Since we have natural numbers, we'll have all functions from natural numbers to natural numbers, and from natural numbers to bool, and bool to natural numbers. And then we just build this up recursively, and this gives us a countable collection of disjoint sets that we can think of naively as our types. And then any element of any of those types is what we will call a term. So we have types, which are these different disjoint sets, and then we have terms, which are the elements. And what we want to imagine is trying to do mathematics using nothing but these particular types and the elements of those types, those terms, and nothing else. So we just throw out the rest of set theory, we throw out the rest of Zermelo-Fraenkel set theory, and try to do all of mathematics just using types and terms. And so that's the naive picture we should have. And now I'm going to forget about Zermelo-Fraenkel set theory for a moment. And now we're going to construct, with that mental image of what it is that we want to construct, we're going to now create a foundational system for mathematics based on that picture. So we're going to have a type system, and we're going to have terms. Every term is going to have a type, and that will be the system that we'll use to do mathematics instead of traditional set theory. Okay, so let's do it. So higher order logic is one of many proposed foundations for doing mathematics. It's simply typed lambda calculus. And now we just think of the types abstractly. They're not sets anymore inside Zermelo-Fraenkel set theory. We're just creating a new formal system that's will introduce its own rules of logic, its own mathematical axioms, and we'll do everything on the computer based off that new formal system. So we'll have two basic types, the Booleans and I, which will my notation for some infinite type is how we'll think of it. And a type can be a constant, or we can have variables standing for types, or we can have arrow types, which intuitively, naively, we think of them as the functions. If x and y are types, we think of x to y as the type of functions from x to y. So every term, there are just four ways of creating terms. They're either constants, variables. We can apply a function to an argument, or there's what's called lambda abstraction. So this is if we have a function body and we have a variable x, we can create the function sending x to that function body. So that is the basic language that we'll use for the foundations of mathematics. And then we're going to create theorems inside this formal system. So a theorem is going to be represented as a sequent. A sequent is just a finite set of assumptions and conclusion. So these are going to be terms, a finite set of terms that are all Boolean types, so they're true or false, and the conclusion will also be a Boolean term. And then a theorem is a sequent that can be deduced from the mathematical axioms or the rules of inference. So I'll just give you briefly, I won't spend much time on it, but there are 10, in this system, there are 10 rules of inference. And with the basic rules of logic, you want them to be very simple, sort of intuitive things that you wouldn't want to challenge. For instance, the reflexive law of equality should hold for any term. That term should equal itself, okay? Not too controversial. Or the law of transitivity, that A is equal to B and B is equal to C, then A should equal C. So these rules of logic are just expressing what it is that we understand by equality. Or if you have two functions that are equal and they're applied to two terms that are equal, then the functions applied to the terms should be equal as well. If you have two function bodies that are equal, then they give equal functions. If you apply a function that sends x to something and you apply it to x, then you should get that something back. So these are all, without going into details, just the sorts of things you would be glad to accept as the axioms. And then it also has a mechanism for doing substitutions of things in for variables. And there's also a mechanism for extending the system by adding new definitions. So that's the whole system. Just those types, those terms, these rules of logic, that's all that we allow ourselves to use in building up results, like the prime number theorem or Brouwer's fixed point theorem and so forth. So first thing we might want to ask is whether this formal system that we've written down is consistent or not. And so I'll just state the theorem. Yes, if Zermelo-Fraenkel choice is a consistent set of, if that's a consistent system, then higher order logic, as I've just explained it, is also consistent. In fact, I've basically given you the proof already, because to give a proof of the consistency inside Zermelo-Fraenkel, what you want to do is construct a model of higher order logic inside set theory. So we need a set that represents the bools. Well, in that example I gave, and I've just copied it back up here, that's exactly what I did. I wrote down a set that had two elements. That's going to be our interpretation of this abstract Boolean type. And we had another type that was to represent an infinite type. Well, I wrote down the natural numbers. Well, that can be used as the interpretation of this type. And then I said, we'll also put in functions between these recursively. And that's exactly what we had over in our type system, is that we were building up recursively from these two basic types. So that gives us an interpretation of higher order logic inside set theory. And we'll say that a sequent is logically valid if for any valuation. So evaluation is just going over into this model, but also assigning to each variable, we need to fix which type each variable type gets sent to, and so forth. So we just fix the variables and send it over to the model, and we'll say that a sequent is valid if for every valuation, if the assumptions evaluate to true, then the conclusion also evaluates to true. And so then to show that whole light is consistent, what you do is you just run through all the rules of logic and show that they preserve validity, and you run through the different axioms of the system and show that they are all valid as well. And then you know that every theorem inside the system is logically valid. And then you just, to show that it's consistent, you have to show that you don't get a falsehood. You have to show that false is not logically valid. And so those are the steps involved in showing that this system is consistent. And this is all just very basic model theory. So you just run through each of these rules of logic step by step, and there are just no problems. It just goes straight through that you see that that this is a consistent system. So they're actually, so it's much nicer than Zermelo-Frankel choice because there are only 3 mathematical axioms. There's the axiom of extensionality that says that if 2 functions are equal on their inputs, then the functions are equal. And there's the axiom of infinity that gives something that's infinite. And then there's the axiom of choice. And that's all you need in terms of mathematical axioms, to make this system work. So you just check off, why do you have the axiom of infinity? Well, you have the axiom of that is valid because we have this infinite set natural numbers in our model. Why is the axiom of extensionality true in our model? Well, this is true in sets, so it holds in our model. Why do we have axiom of choice? Well, also we have Zermelo-Frankel choice. We're taking a set theory with choice. And so we can just easily check off the 3 axioms. So in this way, we prove consistency. Okay, now if we were mathematicians, this is where we would stop, right? We would say we have a consistent foundational system. So what else is there to do? We just prove theorems. But now, if we're doing this by computer, the next thing we want to do is implement this into a computer. This has been implemented using a computer programming language called OCaml. Now, OCaml is one of the dialects of language ML, which stands for meta language. This language was developed as people were doing formal proofs and wanted a language to automate proof scripts. So this isn't just an arbitrary programming language out there. This is a language that was developed specifically with mathematics in mind and formal mathematical reasoning in mind. And many of the same researchers who have been involved in the development of formal proof assistance were involved in the development of this language ML. And as a result, we have a computer programming language that can withstand very intense mathematical scrutiny. It's been very carefully designed from a mathematical point of view. And here I just show a few parallels that the programming language and the syntax of the logic that we're using to do our mathematical proofs, these are very similar to each other. So when you're writing the code to implement the proof assistant, it's almost like you're programming it inside itself because you're using a language that's so close. So to show you that formal proofs go much further than mere rigor, let's look at the proof of consistency of Holite, and let's take that much further. So I claim there are good reasons to believe that there's not a single bug in the implementation of this computer program. It'd be disastrous if you wrote down one of the axioms of mathematics incorrectly, because then you could prove anything, right? So you want to make sure that there's not a single bug in your system. So first reason is that the kernel is remarkably small. So for instance, I told you about the type system, how the terms work, and how the theorems work as a sequence. You might think that might take, thousands of lines of code or something to write that all out by computer. It takes 7 lines of computer code to say what all of the type system is, what all of the terms are, and what theorems are inside the system. So it's an extremely compact, expressive language that allows you to write down this much of the foundations in just 7 lines. The entire kernel takes only about 400 lines of computer code. And if you've written computer programs, you know that that's an extremely small amount of computer code, especially since you're putting all of the foundations of mathematics now into the computer with just this small amount of computer code. So we're going to read over it. I've put it on 3 slides. This is sort of the expanded version. John Harrison, who implemented this, has a T-shirt that has it all on the front side and on the back side, giving the foundations of higher order logic. Okay, but we don't need to stop there. The code has been written in a clean, readable style. I didn't zoom in on it, but I mean, it really is something that you can sit down and read and study and check mathematically to see if it has any bugs or not. It's been checked by many computer scientists, logicians, mathematicians, and I can claim to be one of the people who's looked over this code very carefully. And I personally believe that there's not a single bug in the system. But that isn't where it stops. Since we can do formal proofs, and since we're making a mathematical claim, why not give a formal proof inside our formal proof assistant that there's no bugs in the implementation of the computer code? Okay, so this has actually been carried out. You need to add a large cardinal to avoid Gödel-type problems here. But just basically this model that I described in set theory can also be done as a model inside itself, where you just add this large cardinal to make that's big enough to contain all of the types of your system. And once you do that, then there's no problem writing down the same proof. But this is a better proof than the one that I gave you up on the screen a moment ago for a couple of reasons. First, I just gave a sketch of a proof. And inside a formal proof assistant, sketches aren't allowed, right? You're required to write down all of the steps in all the gory detail when you're doing a formalization. And so that was done with whole inside whole to show that it had no bugs. But it goes even further, because you're not just verifying that the abstract logic does not have any contradiction in it, but you're proving at the same time that the implementation in code is bug-free. So this is going much further than what mathematicians would traditionally do, because you're proving not just abstractly, but in terms of the implementation as well. And so you say, well, okay, so what if whole light has a contradiction, and you're using the contradiction to prove the contradiction, right? So as extra validation of what was done here, you can automatically translate the proof from one formal proof system into other formal proof systems, and then you get cross-validation that these other proof assistants would also have to have contradictions in them, making it possible to make a fake proof of consistency. So things do not stop there. When you do things by computer, you want to know not just that the program doesn't have bugs, but there are much broader questions of, does your operating system have problems that might create a bug? Maybe the compiler is incorrect, so the code was written down correctly, but then it compiles incorrectly. Maybe there are hardware problems so that everything looks correct, but then there's a problem at the hardware level. And so these issues should really be big concern to mathematicians, especially as we start to shift, abstract formal mathematics from paper over to computer. So there's a project, and the current working goal is to create an unbroken chain that goes all the way from whole light all the way down to the level of machine code that has been formally verified at every stage. So some of you may have heard of the project of Leroy doing formal verification of a C compiler. There's a SCL4 project doing a formal verification of the microkernel of an operating system. There's a CakeML project Cake ML is another dialect of this language ML that I've been talking about. It's really their goal to make this unbroken chain that goes all the way from higher order logic all the way down to machine code. And now they've done better than this hole-in-hole verification that I talked about earlier. Now they write down the operational semantics of the programming language, and they write it down formally, and then they make the verification of the correctness of whole light relative to these formally defined semantics of the language. So they're really, I just don't see any way you can get past all of these levels of scrutiny and still have a bug anywhere in the code. Okay, so that was the first part of the outline. I hope to have convinced you with that first part that people are thinking very seriously about trying to implement mathematics like computer in a way that's completely reliable and completely bug-free. Now let's turn to the second part of formalizing advanced mathematics with Coq. So this is a project that I'm going to talk about that was led by Georges Gonthier to give a formal proof of the odd order theorem in group theory. This is a theorem of Feit and Thompson, the odd order theorem. All finite groups of odd order are solvable. This was a very complicated proof in group theory. The proof runs 255 pages. It's not an elementary proof by any means. Thompson's won every major award in mathematics for his work on this problem and related problems in group theory. So here we see that we're really doing a formal proof of something that the mathematicians can respect very highly. And if we look at the broader significance of this, I mean, this is the result that really gave people in finite group theory the permission to write long, complicated proofs that eventually started this big avalanche of papers that led to the classification of finite simple groups. And while no serious questions have been raised about the odd order theorem, the classification result was very sharply criticized by a number of mathematicians because the announcement of the completion of the project was made around 1981, 1982, but the final publication of the classification of the quasi-thin groups didn't come until decades later. And so what this project shows you is that you really, it plants a flag in this project and shows you that really you can check this type of mathematics at the level of the foundations extremely thoroughly. So just to give a broad outline, I'm not going to go into the details of the proof of the odd order theorem in any detail. There was a second generation pass, still based on the same basic outline of the original Feit-Thompson proof that's contained in these two books. One is the local analysis. The other book is character theory for the odd order theorem. So the formal proof project was based on these two books together with all of the background material in algebra that you need as preliminaries to work your way up to these two particular books. So I've listed here some of the background material, textbooks such as Gorenstein's book, Aschbacher's book, Isaac's book on character theory. Basically undergraduate to graduate level algebra covering rings, modules, fields, Galois theory, Wedderburn's theorems, results about character theory, Frobenius reciprocity, orthogonality relations for characters, this sort of thing. So this, before you do the books, first you do formal proofs of all of this background material, building up the foundations to this level of algebra, and then the last part is doing the actual formalization of the two books. So as I understand it, about 2/3 of the work went into the preliminary material, building up the foundations and the notations and everything. And once all of that got built up, the actual formalization of the Feit-Thompson proof proper went quite quickly. So if you go to the odd order theorem webpage, you see this massive graph of all of the different files that make up the proof of the odd order theorem. I've drawn a few arrows to sort of guide you around what the different files are. So up at the top, we get the final file containing the proof of the odd order theorem. Down at the bottom, these are sort of the foundational files setting up what Boolean numbers are and natural numbers are and finite types and using choice. So we start to move up a little bit. We get files dealing with general morphisms and permutations and what are prime numbers. Off to the right, we get basic group theory with centralizers and commutators and CELO subgroups and HALES subgroups, alternating symmetric groups. And then there's the field theory that we need. This is mostly for the character theory and so forth. And then going up in a couple of columns, we get the actual formalization of the two books. So this is all done inside the Koch formal proof system. So if I zoom in on the right-hand corner and everything, so this isn't live here in this presentation, but if you go to the internet, you can click on anything and you open up the files and you want any definitions, you just click on those and it's all cross-referenced and all hyperlinked, so you can just explore through all the definitions that come up in the proof of the Feit-Thompson theorem. So for instance, we get G series. I think this is about derived series and central series and chief series and so forth. Proof of the Jordan-Holder theorem, results about nilpotent groups, the CELO theorems. Above that, elementary structure of elementary facts about elementary abelian groups. Alt is results about alternating and symmetric groups. Bernstein app, this is a combinatorial formula for colorings of squares and cubes that come up. Hall, this is about Hall subgroups, and then we see cyclotomic fields and so forth going up. So if I just click on one of these, say if I click on Hall here, it opens up to the file on Hall, and now you see results about Hall subgroups all expressed now in the notation of this formal proof language. And this isn't just writing down the formal statements of the results, but then also all of the proofs of all of the results are done formally all the way back down to the foundations. So for here, for instance, we've got the Shor-Zassenhaus theorem saying that if we have a Hall subgroup, then all of the then it actually splits, so we get a semi-direct product. Second Shor-Zassenhaus result saying that we've got a semi-direct product saying all of the complements, if the group itself is solvable, all of the complements are conjugate. Then down here at the bottom, corollary, we get the existence of Hall subgroups for solvable groups and so forth. All of this formalized inside our system. And I want to stress that this differs in a fundamental way from what is happening in computer algebra systems such as GAP or Maxima or Mathematica or SAGE, because those, people just write computer code that may have bugs, that may not, who knows? You don't know what the foundations are. You just put in a calculation. You have to trust what you get out. Here, everything really is grounded in the fundamentals of mathematics so that there's there's just a much greater degree of mathematical reliability than what goes on in computer algebra systems. So if we were to take the proof of Feit-Thompson as it's done inside Coq and then translate it back into a paper proof, the single biggest difference that we would notice is that the formal proof is done in constructive logic rather than classical logic. So that means that the law of excluded middle is not accepted as a general principle. If you use it, you need to justify its use. So there are several strategies that were used in doing the translation from the classical proof into a constructive proof, and I'll mention just a few of those. For one thing, so the proof itself, it starts out as proof by contradiction. You assume that you have a minimal counterexample, so this will be a finite simple group of odd order such that all of its subgroups are solvable. And so instead of arguing by contradiction, you can just rewrite it so that everything's done in terms of inductions instead of a negative argument. The character theory part of the proof relies heavily on vector spaces over the complex numbers. This instead is done constructively. It's easier to construct an algebraic closure of the rational numbers rather than taking the algebraically closed field complex numbers. And so you just create an explicit sequence of splitting fields that you take their union and you get an algebraic closure of the rational numbers. Conjugation is used in an essential way of the complex numbers relative to the real numbers. Here again, you do it constructively by constructing a maximal real closed field of the complex numbers, of the algebraic closure. Some constructions are based on decision procedures. For instance, there's a decision procedure. Any statements you write down in the first order language of algebraically closed fields, there's a decision procedure for it, so it can be answered yes or no. This decision procedure gets used in things such as the definition of a socle of a module that's defined as the sum of the simple modules, but you want this to be a constructive definition, and so you find that you can express this as a first-order property and then use this decision procedure to justify your definition. Some places you really just want to use classical logic, and there are these ways of embedding classical logic into constructive logic. This gets used in the proof of the odd order theorem in various places. Then you just have to be careful that the final statement of the odd order theorem is a constructive statement inside Coq. And so you just, whenever you use classical reasoning, you just need to make sure that those bits of classical reasoning get eliminated by the final end of the proof. Coq has a couple of funny features. So I described whole light in the first part of the talk, and I'm not going to go into detail about Coq, but it's got some funny features like function extensionality does not hold generally in Coq. You cannot prove that two functions are equal even if they're known to have equal values on equal arguments all the time. So that's a bit of a pain. You don't have a good theory of quotients, and in finite group theory you're taking quotient groups all the time. And so you really want a mechanism for taking genuine quotients inside Coq. And the way Gonthier sets this up is he's got finite, what he calls finite types with decidable equality. And so he sets up certain types where equality is decidable, and inside those types you can prove function extensionality and you can prove the existence of genuine quotients, and then inside this finite setting of finite groups you always can do things the way you want. But in particular, they don't do the general theory of quotients for arbitrary groups and so forth. It's just in this finite setting. And the last comment follows advantages. Sometimes you want to forget about the type theory. Whenever you have arguments involving finitely many finite groups, it's sort of a pain for each of these groups to have a different type, and for you to have to actually write down different binary operations on each of these groups and write down explicitly the embeddings or homomorphisms between each of these. And so there's a trick that he uses that gets used quite frequently, and that is whenever you have finitely many groups, you can embed them in all as subgroups of some larger group so that they have a common type and common binary operation. Okay, so now turning to the last part of the talk, I just want to talk a few minutes about automation of formal proofs. We've talked about taking things all the way down to the foundations and doing things in a very advanced mathematics. But unless we have a lot of automation, we end up doing a lot of this by hand that we would rather have the computer do. So let's do this. So we don't have any general decision procedures in mathematics. Some decision procedures, just to mention a couple, like Pressburger arithmetic or quantifier elimination for real closed fields. These are pretty slow algorithms, so in practice they're not terribly useful for doing formal proofs. Something that is very useful is Grosvenor basis type methods. I've just given a quick example of proving an isogeny of elliptic curves. These methods have been implemented in major proof assistants so that you just type a single line to get a proof of a statement like this. And the computer, it's all mechanized, so it knows which axioms to invoke and which rules of logic to use to implement Grosvenor basis algorithms and so forth. Another thing that gets used is SAD and SMT type reasoning. I have so these are statements in propositional logic where you're replacing the propositional variables with predicates from some theory, and they're good algorithms to give completely automated proofs of things. So I just took an example that comes up in the proof of the odd order theorem. One particular argument in the character theory part says, suppose we have a matrix, and every entry of that matrix is a virtual character, and we know that each of those virtual characters is a linear combination of exactly 3 irreducible representations with sign +1 or -1. And if we have inner product relations that say if we take any 2 different elements in a row or any 2 different elements in the column, those inner products are always 1. And if we take things in different rows or different columns, then those inner products are always 0. Then the conclusion is that in every column, every entry of every column has an irreducible character that appears in every entry in that column. So this is part of the formalization. You need to give a proof of this lemma. In the book, it's just done as well, the way a mathematician would do. You figure out certain symmetries that might be there. You prove a series of lemmas, and eventually you grind out a result. But if you think about it, it's clear that there are only finitely many possibilities for how we've just got a finite. It comes down to just looking at the 4x2 case. And it really doesn't matter what the characters are. It just matters that they're irreducible and what the inner product relations are. So you don't have to look at the explicit characters. You just need to know that they satisfy certain orthogonality relations. And then there are just finitely many ways to label the different irreducible characters. And so you can write this out as a 2,330 line SAT problem where you just want to know. So here we've got a variable for every entry of a 4x2 matrix. So the first 2 entries, like I have B, ijk. The ij is giving the entry in the matrix, and the k is giving the first irreducible character, the second irreducible character, and the third irreducible character. And then we've got s's giving the signs, and we want to know whether something is satisfiable or not. So you just generate the program, run it, and you're done. All right, so that's how it is done in the formal proof as opposed to the book proof. A lot of other things you can do. Here's just an example of proving nonlinear inequalities using completely automated. So here's a nonlinear inequality that is asserting that the dihedral angle of a simplex is between certain bounds when the edges of the simplex are between certain bounds. And this has been programmed in such a way that you just type in the definitions and you type in the inequality you want to prove, you hit return, and it gives a completely automated proof all the way down to the foundations that this inequality is valid. You can do a similar thing with linear programs. You can take linear programs involving thousands of variables and thousands of constraints. And again, you just generate the linear programs, and the methods have been programmed into the formal proof systems to take those problems and automatically give a certificate inside the formal proof system of the solution. So just a final example using there are methods of proof in first order logic that are quite powerful. You can ask for methods that are, there are no full decision procedures, but you can ask for methods that are refutation complete. So you have a first order formula that is not satisfiable. You want the computer to return a proof that it is not satisfiable. And I'll just skip this slide, but I'll mention in conclusion the sledgehammer technique. So Larry Paulson at Cambridge has been a strong advocate of this method. What you do is we've now got libraries of formal proofs of theorems of tens of thousands of lemmas and theorems that are inside the system. And so you want the computer to automatically go through all of the libraries. You want to prove a new result. You want it to sort through all of these libraries and find the lemmas and theorems that are relevant and put those together to find a proof of the result. And so what you do is you just take all of these libraries and you ship them off to these first order theorem provers and wait for it to find the solution for you. You can actually do better if you do some intelligent filtering of the theorems beforehand. So for instance, if you're trying to prove a result in trigonometry, you might suspect that other theorems in trigonometry would be more relevant than some completely distant field. So you do that. Recent work by Urban and Kalisic have been focused on now applying machine learning techniques to try to intelligently filter through these big libraries of results that you've already proved to find the results that are relevant for a new given proof. So just one example, this is a trivial result. The convex hull of any 3 points in R3 has a set of measure 0. So this is now a fully automated proof. It looks through the libraries and it finds the result that says, oh, the convex hull is a subset of the affine hull. It finds the fact the affine hull of 3 points is a set of measure 0, and it finds the fact that a subset of a set of measure 0 has measure 0. So it turns out that all of the necessary facts were already there in libraries, and in a completely automated way, it's able to find those lemmas that are relevant and reconstruct a proof for you. So the statistics, this will be my last slide, they can now, in the Mizar system, give fully automated proof of 40% of the theorems in the library, 47% of the results in the whole flyspeck library, and comparable results in Isabelle. So I think this is a promising theorem for a promising approach to automation. So thank you very much.
thank you for a wonderful talk. Yes, in my name. Well, I suppose everybody else thinks the same, but you mentioned that the law of the excluded middle is something you could not use in the proof about groups of odd order. Is that something that is the case throughout in formal proofs? Is it a limitation of the system as it nowadays stands? Or is it just a philosophical choice?
So some proof assistants use classical reasoning. Some of the systems use constructive logic. The whole light that I described at the beginning uses the axiom of choice, and that forces it to be a classical system. Coq is a constructive system. It's that way by choice. So it's
a philosophical
part of the
choice,
design
yeah.
It makes it possible for to execute things on the computer when you do it classically.
So it's a part of system design that depends in part
Yes.
on philosophical choices.
Yes.
Does it depend only on philosophical choices, or are there further advantages to a constructive system?
Well, I mean, from a computational point of view, it has constructive logic has big advantages, right? That it computes.
Okay. I have a second question. So you mentioned at the end sledgehammers and other, heuristic tools to find automated proofs. Of course, all of those can be very potent, but they are not guaranteed to yield a result. At the same time, we have areas like when you have quantifier elimination, where in some very particular circumstances, you are guaranteed a proof of every true statement in a very, very, very tiny part of mathematics. Can the second kind of thing, quantifier elimination, say, where it's an algorithmic implementation of the fact, if you wish, that the theory of real closed fields is complete, can that be integrated into this? And is there any hope to what extent is there hope of making the field of application of that second kind of thing larger?
So in my talk, I mentioned algebraically decision procedure for algebraically closed fields that gets used in the proof of odd order theorem. Linear arithmetic gets decision procedures for linear arithmetic get used. But some of the others, like Pressburger and real closed fields, these real closed fields has been implemented, but I don't see it as having great value because it's so slow.
Because what?
It's so slow in practice.
Yes, that is a serious problem. Though when you have a purely existential statement, then it's only singly exponential. But there again, there are problems with implementation in practice.
Yeah.
Do you know whether the two kinds of groups of people are working together? Because I understand that there are people who are working on making this sort of thing for real closed fields faster. But
I don't know specifically.
It's more a comment than a statement. Are you aware of the work by Oscar Lanford about 30 years ago? Oscar Lanford worked on strange attractors, and he proved certain statements, but he relied on very extensive numerical calculation. But he wanted to be sure, that this calculation were right. And he developed for years he worked very hard, going back to what you mentioned, to the hardware. He went back to the hardware, not only the algorithm what he used, but also going to the implementation of the arithmetic code in the compiler and going even to the hardware. So it was very, very similar to your aim. That's what I wanted to mention. So Oscar Lanford was an American, but he spent some years in Paris and then moved to Zurich at 88. Then another comment. You mentioned setoid. That means when you have a set with an equivalence relation, you don't go directly to the quotient. You know that this very similar procedure is very important in higher order categories. Yes. The idea is that the idea is that you could, for instance, a complicated a stack is more or less a groupoid up to some equivalence, and then, but you don't go to the For instance, in order to define a manifold, you have to cover it by a system of shards. But you know very well that you can change the system of shards. So you can encode a covering by chart into a certain groupoid, and then there is an equivalence between Morita equivalence between groupoid, which says that you can go from one chart, one atlas of charts, to another one. And you never actually perform the quotient. And the higher order logic, higher order category is aimed at that. I just wanted to mention it. So it's not surprising that you have to do that.
I just wonder if there is an example of a theorem which was somehow disproved or shown to be false by a proof checker, computer proof checker.
Well,
Can send you some good candidates for that.
so it's my experience in doing formalization that you find hundreds of small errors, but most of these you find before you actually sit down to write out the formal proof. Just as you're preparing to do the formal proof, you see that this is not something that can be formalized, and you have to rework the proof over and over again to put it into the right form. So hundreds of small examples, but I don't know any really big example.
To formalize a proof, do you need to understand it?
I would say now it's in the future it may not be necessary to understand the proofs, but now I think it still is, just because the technology is still so undeveloped.
Do you think the job of mathematician is threatened?
Well, I showed you an example of what full automation can do. Convex hull of 3 points has measure 0. If you feel threatened by that, and yes.
You seemed committed during your talk to showing us that there's diverse mathematics that can be implemented by these proof checkers. And I wonder if there are parts of mathematics that have, that there's sort of notorious difficulty implementing them in these programs, or if it just seems like it can do everything given enough time.
Of course, there are many different systems. Whole light that I described in the beginning is a fairly minimal system, so something like category theory would be difficult to do inside there, but it's very natural to do that in the context, say, of homotopy type theory. So it really depends on the system that you're using, I think.
What is the chance to prove a theorem that has not yet been proved instead of verifying existing theorem?
So you mean a conjecture that is first proved by computer? Is this? So there's the example of the Robbins conjecture that was first done by computer, that is sort of the standard example that people give. This is a conjecture that comes up in Boolean algebra. You have two different descriptions of what a Boolean algebra is, and this is proving the equivalence. And this mathematicians got stumped on this, and a computer was able to brute force it. But